So
Okay.
welcome back, everyone. And this next speaker doesn't really need an introduction. It's Neel, who will be speaking on machine learning. And just to give some context, this summer, Neel will be working at DeepMind. So he really knows what he's talking about. I'll hand the mic over to Neel. And let's start with the talk.
Thank you very much all for coming out so far today. Highly appreciate it. Remote talks are a bit of a pain, especially with regards to things like interactivity and answering questions. So I'm going to try to leave like a few clear points for people to ask questions and try to limit interactivity to those sections, which will hopefully work out okay. I also have no idea how to give good remote talks, so I would be super interested in hearing feedback on how this went. Okay, so this is going to be a talk on machine learning. Sadly, the word machine learning has become sufficiently overhyped and overloaded that saying that doesn't really mean much. So first, I want to begin by just actually talking about what this talk is about. So, as presumably all of you are aware, machine learning has become surprisingly popular over the last 20 odd years. It's a billion-dollar industry, and it seems to basically be a way for computers to do a bunch of things that it seems surprising that computers can do, like recognizing images, playing Go, like understanding language. If you know normal programming, you know that it's really, really hard to imagine doing this in the kind of regular programming style. And this seems kind of like black magic. And annoyingly, the theory in this area is lagging very far behind the practice, what actually works empirically. But I think there are a bunch of important ideas and intuitions that can help demystify this. And so that's going to be my goal in this talk, to try to like give you the underlying intuitions for why this goes from a bullshit magic problem to something that you could imagine trying to solve. The core question that machine learning is trying to answer is this idea of learning from data, or kind of pattern recognition. So symbolically, it looks like this. But really what this is saying is there's some function that we want to learn, but we can't actually directly observe the function. We can observe the function, but with some kind of error terms attached, like I'm trying to figure out how long it takes me to run around a racetrack, but I can't actually observe the perfect time it would take me, because every time I go for a run, there's a little bit of variance. I might be a bit more tired or a bit less tired than normal. But you can still obviously say meaningful things, because I'm going to take a lot longer to run around a racetrack than Usain Bolt would. So the art of learning from data is how to understand the structure, the like underlying function that isn't affected by this error, and like that Neel is slower than Usain Bolt, while ignoring the noise, like that sometimes Neel takes a little bit longer or a little bit less time to go for a run. And this idea of pattern recognition is something that humans are really, really good at. Like, if you look at this picture, these are like the word love in a bunch of different fonts. This one has a ton of noise because it's really obscured, and yet when I look at this, it's blindingly obvious to me what these words say. And like, I presume that none of you have actually seen these exact fonts before, but you've learned how to read as a kid. And what you were essentially doing when you were learning how to read is you were seeing lots and lots of examples of the word love and like the letter L. And then you generalize from this to just the arbitrary idea of what words are, such that even when you see some garbage like this, you can clearly see what's hidden beneath that. And this core problem of learning from data, or pattern recognition, is what the field of machine learning is set out to solve. And again, the core question is this idea of function approximation. So why is this a hard problem? So the reason this is hard comes down to these two core ideas of overfitting and underfitting. What does this actually mean? So let's take this graph of 5 data points. When I look at this graph, it seems pretty clear that they follow a curve like this. this is interesting, because if I drew a really weird wiggly curve like this would fit the curve a lot better. Yet, when I look at it, it's just blindingly obvious that this is a good fit, this is dumb. This is dumb side is what's called overfitting, because I haven't just learned what the underlying structure of the data is, this like nice beautiful curve. I've also learned what the noise is, the like random jiggles up and down that deviate from the curve. And when I say it like this, it sounds kind of obvious. You want to learn the structure and you don't want to learn the noise. But the really, really hard problem is that structure and noise look the same. Like, if I just look at these 5 data points and I don't have any kind of curve guiding me, I need a way to distinguish between sensible and silly. There's also this idea of underfitting, which is like not learning enough of the structure. Like I just completely missed the structure. Generally, that's not that hard a problem to avoid, so I'm mostly going to focus on overfitting, but these are two both really important problems to avoid. And yeah, so avoiding overfitting is really hard because they look exactly the same. So in order to distinguish the structure and the noise, we need to find something that is systematically different about structure and noise. This is what I'm going to call our prior. Like, when I looked at this data, I had this intuition of this curve is nice, this curve is dumb. The sense of like, this is dumb or this fits well is a prior. It's an idea that in nature, more things look like this smooth curve than look like this weird wiggly crap. And you can't just get this from looking at the data, you also need to have some knowledge about what the world looks like. This is the core intuition we're going to be coming back to again and again throughout this talk. So it's like really important to get this idea straight in your head. Structure and noise look the same, we only care about structure, and so we need to understand some way that structure systematically differs from noise. And I find this a bit unintuitive, because the obvious metric to use is just what is my error? I'm trying to get error as low as possible. But actually, this bullshit curve has much lower error than this curve. So you need to somehow balance and be more creative. And this is hard. To give an illustration of why just minimizing error can get you stupid things, take this graph, showing that per capita cheese consumption correlates almost perfectly with the number of people who die by becoming tangled in their bedsheets, which I got from a beautiful website that just collects a ludicrous amount of spurious correlations. If your sole metric is just how low is the error, you start getting stupid things like this. In some sense, this is like the underlying intuition behind all knowledge seeking. Like, how can you ensure that you understand something that's true and that will remain true in the future, rather than just like learning a bunch of random stuff? So why is this hard to do in normal programming? So I'm going to run with a bit of a slightly silly analogy here. This idea of how would a programmer make a cake recipe? The kind of core gist of normal programming is that you are telling the computer exactly what to do. You've got a problem, you know how to solve the problem in your head, and the skill is to convert this knowledge into like a clear, precise set of instructions. Like, mix a precise amount of ingredients together, and then bake it at 200 degrees for 10 minutes, and then you have a cake. This works quite well for a lot of things. Like, there are tech companies that are worth over $1 trillion, or there were tech companies that are worth over $1 trillion. This is a really big industry, and yet, in some sense, it's kind of dumb. Like, you need to know exactly what the computer has to do. If you're trying to imagine how to do a problem, like, say, recognizing what is a picture of a cat and what is a picture of a dog, that's really hard. I have an intuition of what this is like, but actually putting that down into explicit instructions a computer can follow is really hard. And the solution to this is to invent a new paradigm of programming, like a new way of thinking about programming, which is more like making a recipe template than it is making an actual recipe. We're telling the computer like what the shape of a recipe looks like. Like, we're willing to tell it, you need flour, you need eggs, you need butter. You don't need things like a curtain. And we're telling it that you need to cook it for some amount of time, but rather than telling it what to actually do in all of those places, we're just going to tell it, what does a good cake look like? and then tell it to go off and experiment, and then learn, and try to figure out what kind of figures actually make a good cake. And this is like where the word learning comes from. And it's learning from data, because often you don't want the computer to go off and actually make a cake itself. You want to give it a bunch of like failed cake recipes, or successful cake recipes, give it this idea of what ones are good and which ones aren't, and then ask it to learn what kind of numbers should go in a recipe to make a good cake. A common narrative about machine learning is that it's just a magic black box. You have data in, some mysterious bullshit happens, and then an answer comes out. And there's like some truth to this. The reason that people say this is that all the computer has, all the humans see is this template, and then some magic numbers flow in. But the human doesn't know where these numbers came from, or why the computer chose them. All it knows is that it told the computer what a good cake looked like, and then gave it a bunch of data and told it to go off and learn things. Personally, I think that this point about being an impenetrable black box gets a little bit overblown. The right lesson to take from this isn't that it's an impenetrable black box, it's that it's a black box by default. Like, when I look at these numbers, I don't know what they mean, but this doesn't mean that the information is like fundamentally beyond my reach. It just means that I need to try harder. To illustrate this, there was a fascinating paper analyzing what's called ImageNet, which is a really successful image recognizer and classifier. And what they did, on a really high level, is so the image classifier is a layered neural network, which basically means data comes in, it does some processing, that's layer 1, it does some more processing, that's layer 2, and it does this processing like 30 times. And then at the end, you magically get told it's a bird or a cat or a plane. And what this paper did is it tried to analyze what's actually going on in these layers. And what they did was they looked at the images and they tried to figure out which pictures made which bit of the neural network like light up a lot. Like, what was that bit of the neural network recognizing? And what they found is that at the start of the neural network, it was recognizing really basic shapes, like these kind of slanted lines at different angles. Then when you get a few layers deeper, and you start becoming actually able to analyze things, the things that are triggering parts of the neural network are like a dog's face, because it's learned how to recognize basic shapes like circles, curves, lines, and then it's gluing them all together. It's pretty clear that there's something that humans can recognize going on here. Like, these are dogs' faces. These are round things with writing on them. These are weird, messed up things with like holes and regularly spaced things on them. So like, understanding what's going on is hard, but personally, I think this is just like a really fascinating thing to look into, and something where we don't yet understand what's going on, but where there's just a lot of room to do further research. Personally, I find this like really exciting, because this is an area where thinking like a mathematician and being good at maths can be really valuable, and is also an area that's really important to the world. Machine learning is really big. It's going to become a lot bigger over the next 20 odd years, and I would personally be incredibly excited if anyone in this audience decided that they wanted to try to actually answer these questions, because it seems really important to understand, like, what does an algorithm to make a good justice system actually do? With that plug aside, let's go back to the actual meat of this talk. So what is my goal in this talk? I'm going to take this motivating example of handwriting recognition. These digits come from a dataset called MNIST, which is a really famous machine learning dataset. This is one of the first true success stories of neural networks, figuring out how to take these 28 by 28 pixel images, convert them to numbers, and then use a neural network to figure out what the numbers are. My goal is to explain like the underlying intuitions behind why this is possible, and more importantly, why this is practical, why there's something a computer can actually do, rather than just something where I conjecture a function should exist somewhere. And finally, to try to address what I call the ocean crossing point. So this is a time I really like for thinking about maths problems, and especially proofs, where if you think about a maths problem as like how to get from point A to point B, getting from London to New York, there's a lot of kind of fiddly details at the start and fiddly details at the end, like how exactly do I get to the airport? Which airport do I go to? How exactly do I get from the airport to my hotel? But there is like one clear, important, difficult thing in this problem, and that is how do I cross the ocean between London and New York? And kind of that's the main thing that matters when you're trying to answer that question. And I think that in general, when thinking about maths problems, there's like a lot of fiddling, a lot of thinking, a lot of fussing with small ideas. But ultimately, there is like one or two big ideas in a problem that take it from impenetrable to solved. And that is the thing I want to focus on. The theme I'm going to come back to again and again in the talk is just where is the ocean crossing point and what I'm talking about? How does this go from impossible to I could kind of see how this is solved? And I think that's something that's often lost when people are discussing machine learning. General health warning. This is a machine learning talk, not a maths talk. And I'm going to be presenting it as such. So what do I actually mean by this? What I mean by this is that machine learning is fundamentally a practical and empirical field. The practice is ahead of the theory. We know how to do a lot of things, and we're not entirely sure exactly why they work. And I'm going to do my best to try to explain some of the important ideas, but there are some bits that I don't quite understand. And that's a problem with me, not with machine learning. It's going to remain a billion-dollar industry, whatever the theory says. In practice, the way this distinction matters is that, as a mathematician, I have a lot of important intuitions. I'm really good at thinking about things like existence proofs, bounds, worst-case scenarios. But these intuitions don't really do me a good service when I'm thinking about a practical field, because there it doesn't just matter to know that a solution exists or that things can't get that bad. What matters is, what is a typical scenario? How can I make this work? How can I get a computer to actually do this? Another important point is that, as a mathematician, I'm very used to thinking in terms of clever ideas. Like, it always feels like things can be solved by just being smarter about it. And this is quite true about machine learning. Like, there's lots of room to be smart, but there's also a lot of other important things that matter, like having a computer that's fast, having a lot of data to learn from. In fact, a lot of the ideas for machine learning and neural networks were invented in the 70s, but it took another 20 to 30 years for people to have powerful enough computers and enough data for them to actually work. With all that aside, the important points from that long ramble, the core goal here is this idea of function approximation. How can I learn from data? How can I recognize patterns? Secondly, the reason this is hard is that there is both structure, this function, and there is noise, the notion of error. And structure and noise look the same when you're looking at data. So the solution to this is to have some idea of what distinguishes the structure from the noise. And this is difficult and important because you need to avoid both overfitting and underfitting. You need to be balanced. And the practical solution to this is that we shift our perspective from telling the computer what to do to telling it how to learn. Are there any questions on that section? So now I want to try to actually go into a bit more detail about what I mean by having a prior over the structure and how you actually can learn from data. So let's take this graph. I think that it's pretty obvious that the right solution to this is something like a straight line, and it's not a curve that carefully fits through every point. That would be a much better demonstration if I could draw straight lines with my graphics tablet, but hopefully you get the idea. When I look at this, I'm seeing this straight line, and I'm being like, that seems like a pretty good fit. And I'm seeing this wiggly line, and I'm saying like, that is a good fit, but that doesn't seem like it fits the data. And that core intuition of this seems dumb and this seems right is exactly what I'm gesturing at when I say having a prior over the structure. More things in nature are straight lines than weird wiggly lines. And so when I see something that looks pretty much like a straight line, the solution is probably constant. Let's find the constant that fits this one. How do I actually do this? If I want to do this formally, I can define this notion of best by quantifying the error, which I'm going to do by defining the error as, how does this pen work? I'm going to define the error as the sum of this constant minus the data point all squared. And it turns out the thing that minimizes this is the mean. And so a pretty natural thing to say is that the mean is the best fit to this data. And this sounds kind of trivial, but this is actually something that we use basically every day. Like, if I want to figure out what mark I think I'm going to get in a test, I can just like look at the last few tests I did, take the average, and look at that. And like, this is just a really simple example of learning from data. A fun variant of this is that this notion of what goodness means, where I chose squared, is actually kind of arbitrary. And I could also instead take the sum of the absolute value rather than the sum of the squares. And it turns out if you define best like that, then the best guess isn't the mean, it's the median. Intuitively, this is because the mean penalizes things being really far away, while the median doesn't really care how far away they are. It's all linear rather than like bigger than linear. This isn't actually important, but I just find it like super, super cute that the mean and the median are both like the most natural way to average with different loss functions. And you can even define the mode like this. If you pick a stupid error function, which is the number of things that aren't equal to c, then the mode is the constant that minimizes error on this data. And yeah, so the point of all that was just, this is a simple example of how learning from data is a meaningful thing that you can actually do. Though I think it's reasonable to see this and be like, that doesn't seem that interesting or that useful. So here's a second example, linear structure. Again, I've got a bunch of data points. I've got this straight orange line, and I've got this like bumpy curve blue line. And when I look at this, I'm like, this is dumb. The blue line is dumb, but the orange line is sensible. Most things in nature are orange lines, straight lines, and they aren't like weird overfit curves. I know I've done something wrong if my model is outputting this weird overfit curve. This is just another example of learning from data. We've got data, we say, that looks pretty damn linear. What's the line that best fits this data? And for anyone who's a 1B stats, this should hopefully be pretty familiar. We formalize error as the sum of the squared distance from the line. And here, y is the y coordinate, x is the x coordinate. Often x will be a vector. A is a coefficient, or a coefficient of matrices, so like a linear map. And beta is a constant vector, the bias. That's just like a kind of constant term. So like here, A would give you the gradient, beta would give you 5, the constant offset. The problem with linear regression is, how can I find the A and beta that minimize the square distance? I.e., given some data, what is the line that best fits the data? And for not very interesting reasons, you can just solve this problem exactly. And you find that that should be a line break. My LaTeX is not on point. You find that there are just like these two precise linear algebra solutions to A and beta. Why is this interesting? Why am I talking about this? This is interesting because this is just like genuinely a really useful technique. This is a way to take a bunch of data, historical data, say, this seems pretty linear. I could believe that a linear model fits this, and use this to predict future data. Further, it's efficiently computable. Like linear algebra isn't that hard to do with a computer. You can apply this to real world problems where x has like hundreds or thousands of coordinates, and it works pretty well. So this can solve like genuinely useful real world problems. Like, I have a bunch of patients who have asthma, and I want to try to predict something about them, like how well they respond to treatment. I can just take a bunch of like biometric readings about them, a bunch of data, stick it into a model, and see if it predicts this. And I have no idea how that aspect of medicine works, but there are a bunch of real-world problems of that flavor where linear models actually work quite well. And the thing I'm gesturing at there is this idea of being expressive. So by being expressive, what I mean is there are a lot of underlying structures that can be represented by a linear map. Like, the constant example was a bit boring because most things aren't constant, but quite a lot of things look approximately linear, making this a genuinely useful technique. For that reason, I think this is like the most interesting part of 1B stats by like an order of magnitude, and I do not know why they didn't emphasize this more when they were teaching it. And again, this is just another example of learning from data. So now I want to take a bit of a step back and try to zoom out and actually look at the common themes there. So the common themes were, one, we wanted to define a hypothesis class, either constants or linear maps. This avoided overfitting because this is a way of imposing a prior over what our structure looks like. We're saying the thing that fits our data is more likely to be a line than it is to be a curve. So we're just going to force it to be a line, because lines look more structure-like. If your function is a line, and your noise is just like a bit above and a bit below, the noise is very, very non-linear. So the best line that fits the noise is probably just the zero constant line, which means that by defining our hypothesis class, we managed to avoid overfitting. Then we defined what good fit meant, like what makes this line a better line than this. The exact details here aren't super important. There's like a lot of sensible goodness of fit functions or loss functions, just ways of quantifying error. I'm going to go with total square distance for the purpose of this talk, but there's lots of other ones that are also quite relevant. And then finally, we had a class of possible models. We had a metric of like goodness, and then we optimized it. We found the model that fit well, and this avoided underfitting because now we've accounted overfitting. We're just taking the linear model that fits our data best. And this is like the core framework that I want you to keep in mind throughout everything that comes, because this is just fundamentally what all learning from data looks like, neural networks and otherwise. This is also like a little bit unsatisfying because these optimizers, so like these two ideas generalize perfectly, but this notion of optimizing, the idea of add up the numbers to take the best constant, and the idea of like do some linear algebra magic to find the line that fits best, these don't really generalize to more interesting hypothesis classes. And we're gonna need more interesting hypothesis classes because it's pretty obvious that something like handwriting recognition isn't gonna succumb to a linear model. We need something more expressive. So we need like a more general notion of optimization. And that brilliant idea is this incredibly simple notion of gradient descent. So gradient descent, I'm sure, is familiar to a lot of you. It's basically just saying, if you've got a curve, like a function, and you want to find a minimum of the function, a pretty good approach is to pick a random point and then differentiate the function at that point. And to say, if I go to the right, I'm increasing. If I go to the left, I'm decreasing. So I'm going to go to the left a bit, because that's going to get me small. Just like take a small step that you know is going to make yourself small, and then repeat. Like that's captured by this recurrence relation. You figure out the direction to go in. That's represented by this like grad symbol. This is the direction of most improvement, or like most not improvement. You multiply it by some magic constant, alpha, the learning rate. This is just something that you need to make up. Different constants can lead to like different performance of this algorithm in ways that are kind of not obvious, and you don't really need to try things out. And then you just like keep shifting. Because we want to get to a minima, we want to minimize error, we're normally going to go in the opposite direction to the gradient, which is why I'm subtracting. And this like really simple seeming technique is a general purpose optimizer. For a very large class of functions, applying this technique will get you a pretty good guess for what an optimum of the function is, as is illustrated by this graph. Like you start here, you just take a bunch of small steps, and then you end up here. And because the gradient at a minima is 0, and the gradient near a minima is like pretty close to 0, you're going to start taking big steps over here, and then slow down, and then just like eventually kind of like either bounce around a bit or just stop at the minima. This is just a process for taking a random point and then getting a pretty good guess what the minima should be.
sorry, just a question.
Yeah.
Gradient descent. Is it not a problem that we can only get like the closest local minimum rather than the global minimum that we're looking for? Is that not an issue?
That's a good question. It's less of an issue than you might think. The reason I'm going to get onto later, the like very high level summary is that we don't really care about gradient descent for one-dimensional things. We care about gradient descent for many-dimensional things. Like here I'm just showing it works 2 dimensions, but it actually, for neural networks, we're going to have millions of parameters. So we're really doing gradient descent on like a 1,000,000-dimensional space. And if you think about it, it gets much harder to get a local optima the more dimensions you have. Like, if you've just got a curve that looks like this, there are lots of local optima. But if you look on this surface, there's like, it's like harder. Like, you can get saddle points like this, but the like underlying intuition here is that a local optima is one where the gradient is 0 in all directions, and you can kind of think of all directions independently, which means that it's much harder to have every direction be like moving, have like gradient 0. So this is a way in which your low-dimensional intuitions, like 1 and 2D, kind of screw you over, because they make gradient descent seem a lot less powerful than it actually turns out to be. There are also some other tricks you can do. You can get ideas of like changing the learning rate. When you're down here, if you've got a small learning rate, you're going to take small steps. And you don't really want that. So what you could do is you could start by taking really big steps. Like, I'm going to step from here to here, or to here to here, and just like bounce around a lot, and then slowly slow down over time. And if you're like bouncing around randomly, it turns out that you're often more likely to end up in like bigger regions than like a small bump, because generally a lot of landscapes look kind of like this, but with like small deviations. So like if you're in here, things go badly, but most of the time they don't. Anyway, the point of this talk isn't to talk about ways that machine learning people actually do things in practice. My goal is just to convince your intuition that this is a thing that can kind of work. Hopefully that made that feel a little bit more compelling.
Yeah, yes, okay, thank you.
Awesome. Furthermore, this process works for linear regression. Why? Because fundamentally the loss function, this like total squared error, is a function of the parameters and a function of the data. The data is fixed, but the parameters are like a thing we can vary. And what ends up happening is that we can just like make our parameters be random numbers, and then differentiate our loss function and say, if we move our offset a little bit down and we make our gradient a little bit more slanty, then we get a little bit lower error. And just keep making lots and lots of steps like that. And this turns out to be pretty much as good as ordinary least squares linear regression. The reason that I'm emphasizing this idea of gradient descent and approximations rather than the beautiful, elegant linear algebra approach is that this is much, much more general. Like, I can come up with a loss function like the sum of the absolute value distance, and the linear algebra approach completely breaks. But this is differentiable, so gradient descent just works totally fine. It turns out that gradient descent is general enough that it can generalize. So to recap the important ideas in that section, our first goal is to define the hypothesis class. And we want this to be expressive enough that it can cover the entire structure. Like, constants weren't enough, linear maps aren't enough. We want something expressive enough to cover the function we want to approximate. We then define what it means to be a good fit or not. That part's normally pretty easy. And then we optimize. And we want this to be efficiently computable. And if it is, then we can just like get a good approximation to our function. Any questions about that? Cool, then I will continue. Apologies, I am terrible at finishing talks on time, so there's no way I'm finishing this by 5. No offense will be taken if people just leave at 5. But chapter 3 is the most exciting chapter by far, so hopefully that'll keep people hooked. So My goal in this chapter is to explain how neural networks fit into this paradigm. Essentially, neural networks are going to be a hypothesis class. We're going to define the notion of error or loss to show what goodness of it means, and we're going to do gradient descent. And that's basically all neural networks are. I think it's useful to get like a complete description of how they actually work, but there's a lot of details in here that are going to seem kind of arbitrary, and some of them are, some of them aren't. But I'm going to try not to get too bogged down in the details, so I'm going to favor kind of skimming through things than like digging in excruciating detail. If this annoys you, feel free to save up questions for the next chapter break. Noting the general things we want our hypothesis class, this idea of neural networks, to be extremely expressive, because our goal here is to make like a universal function approximator. We want it to be able to capture lots and lots of things. There are issues with that, which I'll get to in chapter 3, but for now we just want it to be really expressive, and we want it to be efficiently calculable. And here's what machine learning researchers have come up with. So the first building block is this idea of a neuron. So a neuron has the type signature vector to real, and it's basically a linear map. W is a constant matrix, X is our input data, B is a constant vector. So this is a linear map. And then we apply some non-linear thing called sigma, and that is a neuron. This is just a function. Sigma is here. It's a sigmoid. Function looks like this. The details are really not that important. All that matters for now is that it's a non-linear function. I'll explain in a moment why non-linear matters. Sigmoids can trivially extend to being vector functions, because rather than applying it to like a real, we just apply it to each element of the vector, and that just gets us another vector out. Then we take this idea of neurons and we glue them together into what are called layers. So this is basically making a function between vectors and vectors, where each entry of the output is a different neuron. Each has its own like vector of weights and like bias term, and each has like an individual nonlinear thing. And in combination, you can think of them as just like applying a linear map to this 3D input to get you a 4D output, and then applying a nonlinear function sigma to get you the value of this next layer. The neural network is just, as I'm sure you probably guessed, just gluing a bunch of layers together. So again, a layer is a function from vector of some dimension to vector of some other dimension, where each element of the output is an individual neuron. And the neural network itself is just the composition of a bunch of layer functions. These are two different ways you can think about it. This idea of like repeated function composition, linear, nonlinear for layer 1, linear, nonlinear for layer 2, linear, nonlinear for layer 3. And you can also think of it as a sequential thing, like make Z the value of each layer, and then there's just a recurrence relation where you calculate each layer from the previous one via this pretty simple function. So that's a load of arbitrary nonsense. Why is this interesting? This is interesting because each of these functions is really easy to calculate, so it's efficient. Like, I can just run through a neural network really fast. And secondly, it's expressive. So that's why we have the nonlinear bits, because if you just have like a bunch of linear functions, like say 2 times x plus 1 composed with 3 times x plus 2, like this just expands to another linear function, like 6x plus 5. And that's true of vectors as well, like linear functions composed of linear functions. Well, if you stick nonlinear functions in the middle, you don't get any nice like closure properties like that, which means that the space of things that can be captured by a neural network is really, really big. There's actually a theorem about this called the universal approximation theorem that says if your neural network has just 2 layers, or possibly 3 layers, with enough nodes, you can approximate any function. Another way you could think about this is we know that computers can approximate basically any function, and you can basically set up a neuron to work like a logic gate. Like, you've got a lot of inputs. You can just ignore all but these two and just stick a bunch of weights and biases in the middle to mean that it outputs, like, think of these as 0 or 1 and make it output 0 or 1 depending on what those are. The details aren't interesting. I recommend working through them if you're curious about this kind of thing. But you can basically just embed any computer in a neural network. And obviously things are way more interesting than that because everything's a real number rather than just a binary 0 or 1. So the point of all this is just neural networks are really expressive. Like, they can capture a lot of things. A natural response you might have to this is that a neural network is finite dimensional. We want to approximate arbitrary functions. Arbitrary functions aren't just finite dimensional, they're infinite dimensional. Like, if I want to map the unit interval 0, 1 to itself, that's a vector space which doesn't even have a countable basis. But in practice, we don't actually care about that. Again, machine learning is a practical field, not as much a mathematical field. In practice, the kind of functions we care about approximating are like smooth curves or things with structure, or something where there's like something to be understood. They're not just arbitrary pattern matches between noise. If they were, you fundamentally couldn't learn them from data. And we know that if your function has structure, you can totally approximate it with something finite. Like, here's a graph I drew of like a random quartic curve, and I just put 10 points on it. I drew lines between them, and that's a pretty good approximation. And this idea of like representing with a linear approximation, or piecewise linear approximations, definitely live in finite dimensional spaces. It's a little bit hard to think about neural networks because they live in such a high dimensional space. Often you'll have tens to maybe hundreds of layers. Your inputs will have dimensions in the thousands or millions. There'll be a really high dimensional space that is hard to think about. So I'm trying to give these like 1D and 2D examples because you can visualize that, but these ideas really do transfer. You can approximate like arbitrary functions in many dimensions with this finite dimensional thing of a neural network. So step 2, defining good fit. As before, this isn't super interesting. We call this a loss function. Generally, we do this by looking at what we call the average square distance. The exact function really doesn't matter. One is having something. And this kind of thing, or anything we just add up across terms, turns out to be pretty useful because optimizing is doing gradient descent. And gradient descent involves differentiating. And you want differentiation to be something that's nice. And if you've got a loss function that's like a sum of a bunch of terms, you can just differentiate each term independently, add them all up, and you found the gradient like that. So a pretty natural question to ask is like, why is gradient descent efficient? Like, Neel has said several times that machine learning is a practical field where you care about things that actually work. Why does gradient descent work? Like, calculus is hard. It takes till A-level to learn how to differentiate functions. And you have like this weird nested compositional mess where if you try to expand it out, then things just get really screwed up. I think that the right way to think about this is, well, there's this really nice and elegant algorithm called backpropagation that basically just lets you compute the gradient quite efficiently. And the crux of it is that function composition differentiates really nicely via the chain rule. So what you end up doing is, notice the loss function decomposes, notice this like recurrence relation relating each layer to the next, and that you care about the derivative of the loss function with respect to each layer, but really you can figure that out by finding the derivative of the loss function. You can look at the derivative of like, how does this layer depend on this layer, and just chain rule your way through. I'm deliberately not going into the details, but hopefully these equations give you a kind of gist of there's a bunch of simple algebra, a bunch of linear algebra, and you just kind of tediously work through the coefficients to make sure things work out. And this is something a computer can do really easily. The algorithm is just start here, find the derivative, do a bit of linear algebra to go back one layer, do a bit of linear algebra to go back one layer, and at each step you found out the derivative of the parameters on this layer, go one step back, you found the parameters on this layer, and you can just add this and like get a neural network that's slightly better. That is all that neural networks are. There's a lot of tips and tricks and optimizations that I haven't talked about. Most importantly, one called stochastic gradient descent, which makes the algorithms take like orders of magnitude less time to run. But if you just coded in all of the ideas I've said, you would quite plausibly get a network that can actually recognize handwriting. A natural question you might have is, how does this actually solve real-world problems? Like, you've solved general function approximation between vectors, but who cares about vectors? There's lots of things in the real world that don't look like vectors, like images and text. The kind of key point here is that it's pretty easy to convert things to and from vectors. Like, vectors basically serve as a natural language for comparing things. Here's a nice GIF demonstrating that. You've got this like 28 by 28 pixel image of a number 8, and you can just convert the pixel values to numbers, rearrange the numbers into a vector, and you have your input. To get output, naively, we would want the outputs to be like a discrete thing, a digit between 0 and 9, like one of 10 possible numbers, rather than a vector. There, the idea is to shift from function approximation to distribution approximation. So we output a 10D vector, where each entry represents the probability of each digit. And this is like representing the uncertainty. This actually turns out to be a lot more interesting than just a function, because it's quite easy to get something which looks kind of like a 3 and kind of like a 5, and you'd prefer your network to say, I don't really know, than to really confidently assert 3 or 5. And yeah, you now have all of the ideas to implement handwriting recognition. You could make a neural network that looks something like this. There's like a lot of theory and tricks around the neural network architecture. That's things like the number of layers, how things connect up, how big the layers are. I found that for getting something that just works, picking like fairly random architecture seems to work without putting much thought in. And I thought I had a graph here which showed my result doing handwriting recognition, probably in the next chapter. But yeah, this is all of the ideas for how to practically implement machine learning in neural networks. I think it's reasonable to have a bunch of lingering confusions and questions. So chapter 3 is basically going to be me addressing these. But you could code up everything I've talked about, and it basically works, bar like a few kind of fiddling tricks. So to recap the important ideas, neural networks are interesting hypothesis class for general function approximation. And the key idea is that you're composing a bunch of linear and non-linear functions in what are called layers that go from an input to an output via a bunch of intermediate steps. And this is useful because it gives you something extremely expressive. If you just had linear things, you would only get linear things out, but having the weird non-linear stuff in the middle means that you can approximate basically any function. You can optimize with gradient descent. Backpropagation gives you an efficient algorithm for doing so, and you can convert most problems into functions between vector spaces. Use a neural network to find an approximation to it, and thus have like an okayish attempt at the original problem. And that is fundamentally what the field of machine learning is about. I'm gonna touch on some like high-level questions people might have now. Apologies again for obviously overrunning. But does anyone have any questions about that so far? I will take that as a no and continue. Chapter 3. Why did that work? I promised at the beginning that I was going to try to convey this idea of an ocean crossing point. This idea of like, when does the problem go from that makes no sense to, oh, I kind of see how you solved that. Like, I kind of see why this works. Everything else is just detail. And I don't think it's obvious what the ocean crossing point within all of this was. And I'm now going to do my best to try to convey this. A general health warning before I actually get into this. Machine learning is not yet a solved problem. This is an area of active research. There are a bunch of compelling ideas, but we're a bit confused about this. The fact that it works is a lot more important than the fact that we don't know why it works. All of what I'm about to say might be complete nonsense, and if it is, that's a problem with me, not with the fact that gradient descent works. And this is a technology that's already changed the world in a bunch of actually important and meaningful ways. With that aside, I'm now going to pontificate about why I think this works. Just to recap, the key question was, how do you distinguish between structure and noise? And the solution was to find a way to distinguish between the structure and the noise. For linear regression and for constants, the reason this worked is that our hypothesis class could capture the structure, but it couldn't really capture the noise. Generally, the noise is not a linear function, while the structure is. And that's why things worked. We imposed a prior. But here, I talked at length about how neural networks are general function approximators. So surely they could approximate the noise, because the noise is just another function. Like, why is the function that correctly identifies handwriting, why does that get reached, and not the function which is like, look at the digits I've been given, and completely doesn't generalize out of sample to just general digits? And I think this is a really interesting question. One intuition you might have is, this is complete nonsense. This shouldn't work. We know from polynomials and Lagrangian interpolation that even in 1D, an n-parameter function, a degree n polynomial, can fit any n data points. Here's a demonstration where 6 data points have been perfectly fit by a degree 6 function. In a neural network we had over here, you've got on the order of like tens of thousands of parameters, because you multiply the size of this layer by the size of this layer to get the matrix of weights, and that's like 10,000-ish. And while the number of data inputs could be as low as like a few hundred, and you could still meaningfully learn something. Something seems really weird here. So first off, there's this really important idea of the train-test split. So the idea here is, we want to figure out whether we're overfitting or not. It would be terrible if we were overfitting. We really, really wouldn't want to put any kind of model into production if we didn't know if it was recognizing handwriting in general versus recognizing something really dumb and special about the dataset we put in. And so the obvious litmus test for is this generalizing or not is test it on data it hasn't seen before. So a super, super common idea in machine learning is take some fraction of your data, like 20%, call that your test data, and just do not look at it while you're training. Training meaning like doing gradient descent and choosing the weights of my network. I'm just not going to look at that. All I'm going to do is just check every so often, what's my error like on this test data? I'm not allowed to change anything about myself by looking at that. I just want to track the error. And this distinguishes a function that's overfitting from a function that's fitting well, because a function that fits well has them both go down. A function that's overfitting will generally have the test error just like go off randomly. Like increase, stay the same, is not learning anything meaningful about it. Note that this is all like a sanity check. This doesn't solve the underlying problem of overfitting. This just tells you, am I overfitting or not? It can't help you because you're just throwing away data. In some sense, this actually makes it harder to learn because you've got less data to play with. But it's so important to check that you're actually learning rather than just thinking that you're learning. But this is generally considered worth it. In practice, this is also important because there are a bunch of techniques, e.g. called regularization, that are known to reduce overfitting, and you can apply more or fewer of them depending on how much they diverge. This graph is the squared error that I got when I was training a neural network that I'd written on handwritten digits, and this is super interesting because the squared error, if you don't know anything at all, is 0.9. That's just you put a 10% probability on each digit. That's shown by the blue dotted line. And the green line is the test error, the orange line is the training error. And so clearly I've learned some structure. The test error goes well below the line of if I knew nothing. There's like something smart that I've done and something that I've learned. However, the orange line, the error on the training set, is much, much lower. This is more like 0.07. This is more like 0.037. So it's both overfit and it's learned structure. This is interesting for two reasons. First, it's quite easy to have an intuition about overfitting being something you do or you don't do. This shows that it's on a spectrum, because we've both learned the structure and we've clearly fitted the noise because the error is lower on the training set. If I hadn't overfit at all, the error would be exactly the same because the training and test data would look the same. Like they're from the same distribution. But also, neural networks somehow don't overfit. Like, there is something weird going on. This isn't just complete nonsense. There's something more to be understood. I decided I wanted to actually investigate this idea of why does it learn the structure on the test data, even though the dimensions are so off. And so to test this, I took the graph I had last time, where I had correct labels, and then I took the same dataset and I just randomized all of the labels of the digits. And this graph shows what happens with the training error and the test error, where I just had random labels. Like I went from having structure and some noise to having just complete noise. And this is super interesting because this takes much longer to learn. This is pretty damn good by arbitrary unit of time 70. Yeah, the x-axis represents time. There's something called an epoch, which I don't really want to get into right now. And this took 250, 400 epoch before it became decent. And in fact, the error here, the error on the training set when you had random noise, is a little bit above the final error you got for the out of sample error for correct labels. It is easier to learn the generalized structure, even accounting for overfitting, than it is to learn random noise. It learns slower and it learns worse. So this is super, super interesting because it shows that there's something special about how gradient descent is engaging with structure versus noise. Gradient descent finds it easier to learn the structure than it does to learn just random gibberish. The best intuition I have for explaining this is that the true structure is somehow simpler than random noise, and gradient descent takes less time and finds it easier to get to a simpler function than it does to get to a complicated function. This is kind of just a generalized version of the linear regression intuition. A line is simpler than a wiggly curve. This is fascinating though, because here I formalize what simple meant as is a line, just this discrete binary thing. And here I don't know how to quantify what it means for handwriting recognition to be simpler and random noise to not, yet somehow this neural network has learned this for me. And this is what I think is the ocean crossing point, the fundamental crux of why machine learning works rather than doesn't work. Gradient descent favors simpler structures, and for a lot of the problems that we're trying to use neural networks to attack, the structure that we care about is somehow simpler than the random noise. And I don't have a clear, formal and rigorous explanation of what simplicity means or how to formalize it, but it seems pretty likely that this does exist. When I'm a kid learning to read, I know that I'm looking at a bunch of instances of text, and by the end of it, I've learned how to read. Or I'm seeing pictures of cats and dogs, or actual cats and dogs everywhere, and then Neel now knows how to recognize unfamiliar cats and dogs. There was some structure that I found it easier to learn than just fitting to the noise of all of the cats and dogs that I saw. And this is making it so that neural networks also work. A further test that I ran of this intuition is if a curve which goes through 5 data points is quite complex, a curve that goes through 20 should be a lot more complex. And if complexity makes it harder to learn and increases the final error, then this means that having more data points with random labels should be harder for my neural network to learn. And I tested this, and this is also true. Here's the original graph I had. I was learning on 800 digits for speed. Here's something where I learned on 4,000 digits. And if you compare them, it takes longer to learn on 4,000 digits, and the final error is 0.44 rather than 0.37. So the noise gets more complicated the more data you have, while the structure remains the same, because the structure is just, by definition, the thing that is the same across all data points. And so the structure of handwriting recognition is the same when you have 4,000 digits versus 800, but the noise is much harder to learn. And so even if you have nowhere near enough data points for a kind of information theoretic learning everything, when you have say 4,000 data points and a million parameters, that's a lot better than having 800 data points and a million parameters, because the noise is more complicated and gradient descent penalizes complexity. So yeah, that is my answer to what is the core insight here. Why does machine learning work rather than not work? Anyone have any questions?
So when we do hypothesis testing in stats, right, we have different sets kind of where we think our values might lie, and they have very different dimensions. And in here, is there something like the space of simple functions has a much lower dimension than the space of complicated things, and that's why gradient descent works better in simple stuff? Just because the space is much smaller.
Let's see. So, I think there's some truth to that intuition. In the sense of I think that the space of sensible functions should be a smaller dimension. I'm not sure that should answer this, because if you think of gradient descent to say exploring a 2D space, then you're just exploring in, and you take a special 1D direction. It's no easier to find an arbitrary point on this 1D thing than it is in the 2D space. If the algorithm hasn't somehow learned that this space is special, if it explores further here, then if you tell it to move further in this direction than this direction, then that could help. But you're somehow baking in a prior. The thing that I find fascinating is that you don't need to bake in a prior. It just finds it easier to learn. It finds the simpler subspace on its own, rather than needing you to tell it. And there's a lot of other techniques I'm glossing over for making it easier for the neural network to find the structure you care about. This is a topic called regularization, for people who want to Google this and learn more. You can do tricks say, if you're overfitting to noise, you're more likely to have a bunch of really big weights, because in general you should expect a simple structural function to have small number parameters, while something dumb that overfits might have a million x minus a million and one y, where x and y are pretty correlated. And so something you can do is you can just tell your neural network, this fit is bad if your total size of weights is big. That's another way to push it to favor simpler functions. But the thing I find fascinating is that it kind of does this by default, at least on problems like handwriting recognition. And this is super not what I would have expected. A few other questions that people might have. Your network seemed kind of a bit arbitrary. Sure it's expressive, sure it's efficient, but there's nothing canonical about them. And I completely sympathize with this, because my mathematical instincts get really annoyed with neural networks, because there's no reason that it has to be linear, then nonlinear, then linear, then nonlinear. There's no reason the nonlinear function should be a sigmoid over anything else. There are a bunch of nice things about neural networks. They're really expressive, you can do gradient descent efficiently, linear algebra is beautiful and really easy to run on a computer. They're easy to think about conceptually, and there's been a lot of theoretical progress about different ways to structure a neural network. This idea of architecture, rather than having all nodes connected to all nodes in the next layer, you could instead connect things up like this. This can be a useful technique for analyzing something like time series data, where each data point is at different times, and it's a lot more likely that comparing two things one after another can get you more information than comparing something at t equals 1 and t equals 55 minutes. So there's lots of room to be creative about how you structure your architecture, but none of these are canonical reasons, and I think this is a pretty fair criticism. neural networks just kind of work, but there isn't something God-given about them that would mean that if your goal was to learn from data, you would have to choose neural networks. It seems like potentially plausible there's some alternate universe where some people found a different thing that also have these amazing nice properties. But the fact that neural networks work is what matters.
Sean commented that it feels tautological in terms of not detecting errors because it doesn't learn high-frequency errors. And low-frequency errors get tagged as bad training data. And by high and low frequencies, he meant in the Fourier sense.
Thanks, Larry.
Let's see. So I guess I'm not super sure what you mean by like looking at frequencies and tagging them.
Oh no, I mean by low frequency I mean long wavelength. Well, if we look at one dimension, low frequency is like something that's almost constant over your data set. High frequency meaning something with a lot of wiggles. And because of what you said about gradient descent, it doesn't detect the high frequency errors, and it doesn't learn the high frequency errors, but it will learn the low frequency errors. But then we just call that bad training data. So it feels like saying that it doesn't learn the errors is pretty tautological.
Which means why we call that bad training data?
Because it would just be a systematic bias, and like everything is just all the data points are just like 10. If it's just 1D, everything is just 10 cm longer than it should be. And then that would be a zero frequency error. There would just be no deviation across the entire data set. And that would just be called bad training data.
Sorry, I don't think I really understand the context here well enough to give an informed answer, but happy to message about that afterwards.
Sure, yeah, thanks.
Anyway, so yeah. Why does gradient descent work? I pretty much answered this earlier. There are two intuitions here. So intuitively, you can get stuck in a local optima. Like if you're around here, you're just going to bounce around, and you're never going to realize there's this glorious global optimum over the hill. So this is like a lot less likely in higher dimensions, and you can also do tricks by messing with the learning rate, bouncing out of here and into here. There are like a bunch of techniques for doing this well. Another intuition you might have is that this thing about favoring simplicity over complexity can actually be thought of as falling into a local optima. There is some function that overfits to all of the noise in my dataset, and that has much lower error, but gradient descent doesn't reach it. It instead reaches this like general has actually learned the structure function. And that there is like a better function for the purposes of the training set out there that it isn't reaching is exactly what it means to be in a local optima but not a global optima. This just happens to be quite desirable behavior. So I guess the intuition is just optima are rare, and for a question where there's like some actual structure to be learned, like something where humans can do it, like image recognition, the local optima are sufficiently rare that the closest local optima is the actual structure to be learned, because that's something special. Like our prior over image recognition is that there is something to be understood there, rather than it just being like random crap. And finally, a question you might have, just like, how is this so widely useful? Like, sure, I kind of buy how can this do handwriting recognition, but how can this do sentiment analysis, text generation, spam filtering, recommending YouTube videos, predicting the stock market, drug discovery, all of the random garbage that machine learning firms are doing nowadays? And the insight here is that what we did wasn't solving the problem of handwriting recognition. We came up with an attempted solution to the general problem of pattern recognition and learning from data and learning for things where there is some underlying structure. And that isn't special to handwriting recognition. That's just a general property of lots of things. This is a thing that the human brain is incredibly good at, as something that's like the secret of a lot of our success. And this is an attempt at getting machines that can do that as well. And that's why it's widely useful. So to recap the important ideas there, why don't neural networks overfit? Because the structure for the kinds of problems we care about is less complicated than the noise, and gradient descent favors less complicated hypotheses. And This is our fundamental prior over the structure rather than the noise. And secondly, this mostly holds if you have enough data, because the more data you have, the messier the noise is, and so the harder it is to overfit. This is widely useful because it's a solution to the general problem of learning from data. Ish. There are like a bunch of problems with this and a bunch of like tips and tricks and techniques that actual machine learning practitioners have come up with. And in general, trying to apply just the ideas I've given you to actual real problems frequently messes up. But I roughly think most of that is just fiddling. And this is like the core ideas. And ultimately, the work is being done by having a really expressive hypothesis class and this powerful optimizer of gradient descent. To see how this all fits together, I'm just going to go over the key ideas of this entire thing again. Fundamentally, machine learning is a problem of learning from data, pattern recognition, and distinguishing the structure from the noise. This is hard because structure and noise look the same. You need to know something about the problem to distinguish the two, like in the example of linear regression. Our overall paradigm is to define a hypothesis class, which is a neural network, which had alternate linear and nonlinear bits, which was valuable because it was extremely expressive and could generally approximate most functions. We defined goodness of fit, which is pretty easy and not very interesting, and then we have an optimizer. The optimizer is gradient descent. It's efficient because of this algorithm of backpropagation, and we avoid overfitting because gradient descent favors simpler solutions, and the kinds of problems we care about solving have some simpler structure that can be learned, and is easier to learn than the noise, especially if you have enough data. And yeah, that is my story for why machine learning works. Thank you very much all for coming.
Question from Park. Thank you earlier. Just a couple of questions. If you have infinite data, so one of them from direct, then why you didn't error problems shouldn't exist, and then what would be the goal of machine learning in that case?
Sorry, what do you mean by error wouldn't exist?
You would want the error to be minimized if you have more and more data, right? The random error that is created.
Yes.
Or
I actually don't think you'd want the error to not exist. So a way to think about this that might be a little bit more intuitive. Yeah, so when we look at linear regression, you've pretty clearly got a lot of points that bounce around this line because they have error. And like, in some sense, this is like, you can't do better than this line. Like if you do better than this line, then you're learning noise, not data.
Hi, can I ask a question?
Yeah, go for it.
Yeah, sure. So as you're talking about overfitting and underfitting, and there's a problems about exploration and exploitation, for example, in some kind of sampling, like Markov chain Monte Carlo. And one is about really understanding a small space, understand it really well. And the other is about really knowing the whole universe, the whole space like. So like how do we balance these two things? And because these two things seem quite important, but make like really emphasizing on one thing is not the best thing to have.
So okay, so my impression of the question you're asking is like, one thing you could do is just say, I'm gonna only go to Chinese restaurants, and I'm only gonna go to Chinese restaurants, and I want to just find the best Chinese restaurants. This is a small set. I want to learn it as well as I can. Alternately, you could say, I'm gonna go to all of the restaurants in the world. I'm spreading myself quite thin. I'm gonna have a much larger data set, and it's like much harder to find structure. And that's like a choice that I make. And you're asking, how does overfitting and underfitting translate into that? Is that an accurate summary of your question?
It's kind of, but I want to know like in that kind of question, for example, when we are finding the distribution behind some sort of data, we want to do the Markov chain Monte Carlo, but sometimes if we emphasize some exploitation, maybe we are ignoring the whole structure. If we're like emphasizing exploration, maybe there are some interesting point in some space, but we're not looking at. So how do we balance these two aspects?
So that's a really interesting question. I'd roughly consider it quite outside the scope of the kind of questions I'm talking about. I roughly consider exploration and exploitation to be questions about like how much data do you collect,
Okay.
and say like one way you could think about it is like, say I've got a sine curve. Do I only collect data points between 0 and 1 and get a really good idea of this curve? Or do I collect data points between 0 and 2 pi? It's a much harder curve to learn, but I could get like a rough idea across a more useful space. And so the core point of machine learning and pattern recognition is that you have this desire to generalize your ideas from in-sample to out-of-sample. Generally, you really wouldn't want to be only looking between 0 and 1 if you're later going to have to look between 1 and 2 pi. But if you could make it so you only need to care about between 0 and 1, maybe it's better to look at a smaller thing and do it well. If you need to look across this entire interval, you should obviously be exploring as much as possible. I don't have a good answer to the question of like, how should you explore versus exploiting as a general rule. If like, you don't know whether you want things in here, or maybe you want things over here because it might be even better. There is a broad computer science literature about this.
It depends on your own purpose, what you want to do, right? Like, if it depends on whether you want to explore small space or you want to know, like, in a larger space, what's it talking about? Somehow.
Yeah, it's a difficult question.
Right. Sure. Thank you.
For people interested in the kind of like general audience exploration of that, I'd recommend the book Algorithms to Live By I think Brian Christian, which is just a really good analysis of how you can actually apply ideas from computer science to real-world questions, like how should you explore versus exploiting. Yeah, any other questions?
That's mine, if no one else is asking anything.
The like high frequency, low frequency one?
Right, yeah. Since we're on this slide, like so a low frequency error in this case would be, right, imagine there's a black line underneath your red line, which is like the true function you want to model. And then these blue points, the black line plus some random error, and then your red line is lying on top of the black line in this case. But the low frequency error I was talking about is something like, imagine all the blue points shifted up by 10. And that would be a zero frequency error as a constant shift over the entire range from -20 to 60. And if you look at all those blue points and you do linear regression, you get a red line that's like 10 points higher than this current red line. And that's a massive error, but that would be ascribed to having bad data that doesn't accurately describe the true function. So yeah, so you kind of got it, like all the high frequency errors will get caught by the gradient descent. Low frequency errors will be put up to bad data set. So I mean, it's not actually true that it doesn't learn errors. Right? It just doesn't learn high frequency errors, and then for low frequency errors, you just somehow say that it's not its fault for not learning that. So it feels tautological to say that it doesn't learn errors.
Okay, could I paraphrase that as it doesn't learn complicated errors, but it does learn simple errors?
Sure, yeah. Errors that are as simple or simpler than the underlying function.
Yeah, I think I agree with that. Like, yeah, I agree that if you just like say flipped the labels between 3 and 7, it would learn 3 and 7 the other way around, and that would be the fault of your function. I guess the reason I think this is interesting rather than tautological is that it's doable to remove the low frequency errors before you feed it into your algorithm. And it's hard to remove the high frequency errors. Things like maybe you've got an 8 that looks like this. Maybe there's like a I don't know. There's like a shadow
like
across the side, or like this bit's a little bit distorted and the ink blotched a bit. Like high frequency errors are the interesting things here in this analogy.
Sure, yeah. Okay.
I don't know if that was a satisfying answer, but that's
makes sense. Yeah, thanks.
No worries. Anyway, I apologize for running by over half an hour, but thank you very much all for coming.